Hello, this is section 10.1 scatter plots and coloration. So this is about another area of the inferential statistic involved in determining the weather relationships between the two or more numerical, that is could be the quantitative variables. So for instance, is there a relation between the person's blood pressure and his age or her age? Is there a relation between the size of the house and its appraised value? We will investigate whether there is a linear relationship between the variables. If so, there is a strength of the relationship, and what type of the relationship does exist, and then what predictions might be made from the relationship. In simple correlation and regression studies, data from the two numerical and quantitative variables are collected to study whether the relation exists between the two variables. So data are collected as ordered pairs. So one variable is independent variable, and then the other one should be the dependent variable. So independent variable can be manipulated. It is known as the explanatory variable and called the x, and the dependent variable, which cannot be the control or manipulated, is known as the response variable. We call the y's. So whatever you uh, use as an x, and then y is gonna be automatically comes out as outcomes. The researcher decides which variable can be considered the independent variable and which can be the dependent variable. Sometimes one variable can be assumed to affect the results of the other. For instance, the hours a student studies for the exam is likely have an impact on the percentage of the correct answers on the exam. In this case, the hour study would be the explanatory variable, and the percentage of the correct answer would be the response variable, which is if we spend more hours, and then everybody think that it's a student get the you know the have a more correct answers. However, when the considering the relation between the one income and one's height, it is not clear which should be the independent or which should be the dependent. So the determination is arbitrary. So the independent and dependent variables can be plotted on the graph called the scatter plot. The horizontal axis is labeled with the name of the independent variable, which is x, and the vertical axis is labeled with the name of the should be the dependent variable. Sorry about that. This is typos. Should be the dependent variable. The coordinates of the axis are determined by the smallest to the largest data values of the variable. Okay, let's go to the next page. So scatter plot. Scatter plot is a graph of the ordered pairs x and y of the numbers consisting of the independent variable x and then the dependent variable. Come on, there's a typo again too. Variable y. The scatter plot is a visual way to describe the nature of the relationship between the independent and dependent variables, even if the scales are not the same. So researchers look for the positive linear relationship when the data points increases from the left to the right, the negative linear relationship when the data points decreases from the left to the right. So positive linear relationship is going to be the increases, and then the negative linear relation means the decreases. And then curvilinear relationship or other non-linear relation or non-known relationship at all when the scatter shows no pattern, a line, or a curve. So the first one, this one is actually the positive linear relationship, and this is a negative, right? The slope goes down. Linear relationship. This makes a straight line still, but this is not a line at all. So we're gonna say curvilinear relationship, and then this is actually I don't see any relation as order pairs as all the points, so we just can say it's a no relationship. Procedure of the drawing the scatter plot. So step 1, draw the label and x and y axis, and step 2, plot each point on the point. Step 3, determine the type of the relationship, if any, that exists for the variables. Okay, so let's look at the example 1 to see absences and the final grades. So construct A scatter plot for the data obtained in a study on the number of the absences and the final grades for 7 random selected student statistic classes. So the student who has A, B, C, D, E, F, G, that's what they label. And then the number of the absence for the student A was a 6, and then B was 2, 15, 9, 12, and 5, and 8. And the final grades has 82, 86, 43, 74, 58, and 90, and then 78. So as you notice that the student who has a last absence, like a 2 or 5, who got the 86th grade and the 90 percentage, right? But student who got the most of the absence, like a 15, 43, and then 12, like a 58 AC. So I think that there's some relationship in as a positive, but let's see what kind of graph we're gonna get. So we're gonna plot it in, okay? So X is about the number of absences, and then the vertical axis is the final grades. All right, so the number of absence was a 6 for the first students. It has 82 points. Okay, sorry about that. So 82 points, about 682 is about here. And then the B students got a 2 absence, but the 86. And then the C students got a 15 absence, so that's a lot, right? And then they got a 43. Okay, so 43 about here. And then the D students got a 9 absence, and then the 74. So go up to 74 right here. And then the E student got a 12 absence, and then the 58. So 50, 55 about here. And then the absence got a 5 absence, and then the 90 points. Okay, so about here. And then the G students got an 8 absence, and then the 78. Okay. So what do you think? Do you think this? I think this is kind of too big. So let me get the. Okay, how about here? All right. So what do you think? I think this is actually the, yeah, the linear. Yeah, almost the linear, right? Yeah. Okay, let's look at the next page. Example 2. Number of the teachers in thousands or the number of the pupils per teacher. A researcher wants to check for the relationship between the number of the pupils per teacher and the number of the teachers in thousands employed by the school district. The data are from a randomly selected sample. So there are this first column talking about the district number 1 to up to the 10 districts, and the number of the teachers are there as a 7,000, 34,000, like that. And the pupils in that district was this one. So that those are the students for the per the teacher. Okay, so I wanna actually the plot them in. All right, so the number of teacher for the horizontal axis, and then pupils per teacher is the vertical axis. Okay, so let's see. So district 1. So district 1, and there are 7 teacher, and then there are 12.4 students. It's about 7 point about here. So 12.4. So 12.5 about here. And then district 2 has a 34 number of the teacher, and about here. And then the 14.3 is very close to 15, right? And then the district 3 has a 9 on the number of the teacher, and then the 14.3 is about here. And then the district 4 has 8 students, has a 9.2. Yeah, very close here, right? And then the district 5 has a 16 teachers, and then 18.3. This 16 is about here. So 18.3, which is about here. And then the district 7 has a 6 teachers and 12.3. So 6 teachers, 12.3. So 12.3, yeah, very close to here. And then the District 8 is 14 teachers. Okay, 14 teachers has 12.4. And then the District 9 has 32 teachers. 32 about here, and then 15.2. Yeah, very. And then the District 10 has 10 teachers, has a 13.4. So 13.4, which is about here. Okay. All right. So yeah, this kind of relationship. So do you think that this is as linear too? Kind of, but yeah, it's like a little bit flat. Okay. All right. Let's look at the next page. So coloration coefficient. So coloration coefficient measure in the strength of the relationship between the two variables. Population coloration coefficient. The population coloration coefficient denoted by the rho. This is we call the rho. So this is we call the rho. Is a correlation computed using all the possible pairs of the data value x and y taken from the population. Linear correlation coefficient. The linear correlation coefficient denoted by the R, computed from the sample measures the strength and the directions of the linear relationship between the two quantitative variables. So property of the linear correlation coefficient, number one, the correlation coefficient is a unit last measure. Number, just like a slope. Number two, the value of the R will always to be between the -1 and 1 and inclusive. And then number three, if the values of x and y are interchanges, the value of R is unchanged. Then number four, if the values of x and or y are converted to different scale, then the value of the R is unchanged. Number five, the value of the R is sensitive to outliers, so can change dramatically if they are present in the data. So the graph below shows the relationship between the value of the correlation coefficient and their respective scatter plot. So when you see this kind of the relationship of x and y is about R is about 0.5, which is half, and then actually the values actually get together very narrow down, and then we call those about the 0.90. And now this is almost a linear, right? Yeah, this is almost a line is we call the one. And then this is a negative but very spread out, right? So about negative 0.50, and then very compactive to the negative way, so 0.90 negative. And then this is almost a line is a negative 1.00. All right, let's look at the next page. Assumption for the correlation coefficient. Number one, samples are random sample. Number two, data pair fall approximately on a straight line and are measured at the interval or ratio level. The variables have a variate a normal distribution that is given any specific value of x, and the y values are normally distributed. And given any specific value of a y, the x values are the normally distributed. So we have a formula is right here. Okay, so this is the formula we're going to use for the finding R. So there's a lot of work to do, okay? So procedure for the finding the value in the linear correlation coefficient. So in the formula, we need to get to the value of x and y as x and y order pair. And then there's a place that we need to multiply. So we're going to multiply, but eventually we get the sum. So we need to get a total sum of the product. And then we also need to get the square of x. And then, of course, we need to get a sum of that too. And then we also need the y square. And then we need to add them at the sum too, okay? As a sum, okay? So this, we are going to using a table. So step two. So step one is to make a table. Step two, to fill out the table. So yeah, with those information as a columns. And then we substitute the values in the formulas, right? This is the same formula that I put up there too. Okay, so and the n is the number of the data pair. The R is around to 3 decimal places all the time. Okay, all right, let's look at the next page to see what we can do about this. So from the data in problem 1, the teachers and then the pupils per teacher, compute the linear correlation coefficient. We already have the data, have the noticed that the scatter plot has a negative slope. Oh, so that was kind of negative slope that we can think about it. Okay, so 6 and 82 and 2, 86, 15, 43. Yeah, so this is actually that we can think about it as samples, okay? All right, and then 9 and 74. So we didn't actually take the everything. We take so out of the, yeah. Oh, no, that was the first problems, yeah. So sorry about that. This is about the absences and the final grades, okay? So 6 absences and got a 82% on the final, right? Okay. Okay, so this problem, so I already put down the data. So of course, we need to find the sum. So you need to adding all this number together, adding it up, and then we'll get that as 57. Same as in the second column too. You need to add in all this number together as a percentage, get the sum of the 511. And then you just need to multiply the x and y. So 6 times 82, 2 times 86, okay? So you got to multiply that. You got the product of 492, 172, 645, 666, 696, 450, and then 624, which is get the sum of the two. So add it all together, you got 33,745. For the next one is so we score the x, okay? So you're squaring this whole thing. So like a 6 square, 2 square, 15 square like that, okay? So you get the 36 and 4, 225, 81, 144, 25, and 64. And you also need to square the y too. So you are squaring the y here. So 82 square, 86 square, right? So you get the 6,724. 7,396, 1,849, 5,476, sorry, and 3,300. So yeah, so this is a 6, sorry about that. 6, and then 3,364, 8,100, and 6,084. And then sum of the x squared is 579. Sum of the y squared is 38,993. Now, what you do is we're going to plug it in. So n is, so you got how many pairs? 1, 2, 3, 4, 5, 6, 7 pairs. So n is a 7. So n times, and sigma of the x and y, which is the same as this one, right? So I put the 3,745, subtract, and then we multiply the sigmas of x and sigmas of y together. So sigma x is 57. Sigma of y is 511, okay? So you multiply by 57 times 511, root of, and then bracket of 7 of, and then you need to find the sigma x squared, which is 579. Subtract, and then sigma sub x is 57, but you gotta square it. And then break it open again, so 7 times of sigma y squared, which is 38,993. Subtract of sigma of y is 511 square. And then use a calculator, we'll get the negative 0.944. So how do you conclude this one? So this is this means the linear, the coloration coefficient suggests a strong negative linear relationship between, yeah, it is, the number of absences students have in class and their final grade. So that is, the more absences a student have, the lower the final grade will be. Okay, all right, so that's number 3. Okay, go to the next page. Then now number 4, we are talking about the number of the teachers in thousands and the number of the pupils per teacher. So let's see what it is, okay? So yeah, you just need to fill them into. So I want you actually to practice with this, okay? So yeah, if you do that, so you can just follow the instructions I have from the previous problems, okay? Okay, so do you want me to work with you guys? Okay, so x times y means you should get, well, let me get down there once, okay? 86.8, 486.2, 128.7, 73.6, 292.8, 181.5, 73.8, 173.6, 486.4, 134. And then square 49, 34 squared is 1156, 9 squared 81, 64, 16 squared 256, 225, 36, 196, 1024, and 100. And the y squared is 153.76, 204.49, 204.49, and then 84.64, 334.89, and 146.41, 151.29, 153.76, 231.04, and 179.56. And then let's add them all to each column to get the sum of each. Okay, so 151, 133.9, 2117.4, 3,187, 1,844.33. And then what time to plug it in? So there are 10 pairs, okay? And sigma x at 2,117.4, subtract. Sigma x 151, sigma y is 133.9. Square root of n equal to 10, I'll break it up, right? And then sigma sub x squared is 3,187, subtract sigma sub x, which is 151 square, and then 10 times of sigma sub y squared is 1,844.33, subtract sigma sub y, which is 133.9 square. I got 0.442, right? Okay. All right. Okay, so let's look at the significance of the coloration coefficient. So coloration coefficient is between -1 and 1. So when r is close to either -1 and 1, the linear relationship is strong. When r is near to 0, the linear relationship is weak or does not exist because the value of the r computed from the sample data. There are two possibilities that are when r is not equal to 0. Either the value r is high enough to conclude that there is a significant linear relationship between the two variables, or the value of r is due to the chance. Assumption for the testing the significance for the linear coloration coefficients. Number 1, the data, the quantitative and obtained from a simple random sample. Number 2, scatter plot shows that the data are approximately linear related. Number 3, there are no outlier in the data because the outlier makes the data the problem very seriously dramatically problems. And number 4, the values x and y must be come from the normally distributed population. So the null and alternative hypothesis are, so h of the 0 is a low equal to 0, and h of 1 is a low not equal to 0. So we will discuss their method to test the significance of the coloration coefficient. The first is a traditional method that use a t-test, and the second use the p-value. So third use the table 1 to find the critical value of r for the specific degrees of the freedom and a given significance level. So formula for the t-test for the coloration coefficient is this formulas. Okay, so this is the formulas we are using here. So degree of freedom is this time is n minus 2, where n is the number of the order pair of x and y. So traditional method of the hypothesis testing significance of R. Step 1, state the hypothesis. Number 2, critical value find and compute the test value and make a decision and summarize the result. So same as we did hypothesis testing. Okay. All right. Next page. P-value method for the hypothesis testing significance of R. Step 1. State the hypothesis. Step 2, compute the test value of t. Step 3, find the p-value. And step 4, find the decision. And step 5, summarize the result. And the R method of the hypothesis testing for the significance of R to tail test only this time. Step 1 is state the hypothesis. Step 2, find the critical values of R from table 1. And step 3 is a compute the correlation coefficient R. And then step 4, make the decision. And then the step 5 is summarize the result. Okay, so critical value for the PPMC. So this is actually the table that we are using for the R method. Okay, alrighty. Let's look at the next page. All right, so that's a continuous up to here. So test 5. So test the significance of the correlation coefficient. So we're going to use the number. Problem number 3. Test the significance of the claim that there is a linear correlation between the absences and final grade, and the alpha equal to 0.05. But as you notice, we have R equal to negative 0.944. So for the first one, we need to state the hypothesis no matter what method we use. Okay, so the hypothesis H of 0 is rho is equal to 0. And then rho is not equal to 0. So we're going to use a two-tail, okay? And then method 2, the final critical value for the t is degree of freedom, which is 7 minus 2. And then that's a 5. And then the t value that we use for the alpha equal to 0.05, which is we have to use alpha over 2. We got the plus minus of 2.571, which means on the normal curve, the critical region is less than 2.571 and then greater than 2.571. So this is the critical value. So in step 3, we're going to find the t value, which is r times n minus 2 over 1 minus r squared. So it is, we already find it, 0.944 of n equal to 7 minus 2 of 1 minus of negative 0.944 squared. And then I got negative 6.398, which means is right here, right? About here, negative 6.98. So now, well, can you conclude it in the step 4? So t value is actually t value, which is negative 6.398, which is less than the negative 2.571, which is a critical value. That's why we need to reject, because it falls into the critical region. So null hypothesis. Which means we have to say that there is sufficient evidence to support a significant linear relationship between the number of absences and then final grade. Okay. All right, that's the method 1 using the traditional method, and then the method 2. Compute the test value here. So we know that the t was the same thing. So we use r equal to the n minus 2 over 1 minus r squared. It's r, which is negative 0.944 square root of 7 minus 2 over 1 minus of negative 0.944 square, which comes out as negative 6.398. Okay, and then we use that value using the table, and then p-value is going to be less than 0.01, but we still need to compare that as alpha, which is 0.05. So think about that relation. It is work, right? Yeah. So that's and then because of that, then we'll get the same thing. There is sufficient evidence to support, which is a significant linearity between the number of absences and final grades, okay? Alrighty, and then method 3 is find the critical value R from the table 1. So the table 1, they locate the row of the degree of the freedom, the critical value of the R. So the list for the alpha equals 0.05, and then the or the 0.01. So degree of freedom in here is a 5 with the alpha equal to 0.05. So let's take a look, okay? So I think we had a table here, right? So degree of freedom was 0.05 from the degree of freedom is 5, which is we can say 0.754. Okay, all right, so go there. All right, so this time, but this is a negative relationship, so I have to say the critical value of R is the 0.754, but I have to put the negative, which is R was negative 0.944, and then compare. So R is negative 0.944, and compare that. Is that the less than negative 0.754, which is a critical value? So yes. So that's why I summarize. Reject the null hypothesis, which means we can say there is sufficient evidence to support to a linear relation between the number of the absence and final grades, okay? All right, there's another example that I put for you to try. Okay, so the idea is the same, okay? So this time we're using the number of the teachers and the number of the pupils per teacher, okay? So H of 0 is rho equals to 0, and then H of 1 is rho is not, sorry, should be a rho, not a beta. The rho is not equal to 0, okay? So find the critical value. So this is the degree of freedom of 10 minus 2, which is 8. And then t is about plus minus 2.306. So over here, negative 2.306, positive 2.306. So this is a critical region. All right, so now the test value, which is a t equal to r of n minus 2 over 1 minus r squared, which is 0.442 of 10 minus 2 over 1 minus 0.442 squared, that I got 1.394. So 1.394 is about here, right? 1.394. So it's not in the critical region. So now we have to say that is do not reject the null hypothesis, which means there is not sufficient evidence to support a significant linear relationship between the number of the students and the number of pupils per teacher. Okay. All right, so now compute the test value, which the test value was 1.394. And we're using the p-value this time. So p-value is about a little bit greater than 0.20. Now compare with alpha, which is 0.05, which is not true, right? So we have to do not reject. The null hypothesis, which means there is not sufficient evidence to support. Okay, so now method 3, using R, value of R, right? So degree of freedom is 8, and alpha equal to 0.05. Use a table I, which is a previous table, and critical value of R is 0.632. So now compare the R, which is 1.394, to compare that. Is at the less than the critical value, which is 0.632, which is not. So that's why I do not reject the null hypothesis. Okay, so we have to do the same thing. There is not sufficient evidence. So no matter what method do you use, yeah, we end up the same conclusion. Okay. All right, next page. Possible relationship between the variables. So when a null hypothesis has been rejected for the specific alpha value, any of the following possibility can exist. So number 1, there is a direct cause and effect relationship between the variables. So that is X causes Y. For example, the water causes a plant to grow, poison causes death, and heat causes ice to melt. Heat causes ice to melt. Number 2, there is a reverse cause and effect relation between the variables. So that is a Y cause X. So for example, the researcher may believe that the excessive coffee consumption caused nervousness. But it may be that the nervous person craved the coffee to calm his or her nerve. Number 3, relationship between the variables may be caused by the third variable. For example, if the statistician correlated the number of the deaths due to the drowning and the number of the can of the soft drink consumed daily during the summer, he or she would probably find a significant relationship. However, the soft drink is not necessarily responsible for the death, since the both variables may be related to the heat and humidity. The third variable is a variable that the researcher does not know about, or that is not counted for in the study, is called a looking variable. So there may be the complexity of interrelationship among the many variables. So for example, the researcher may find a significant relation between the student's high school grades and the college grade, but probably many other variables involved, such as IQ, hours of the study, influence of the parents, and motivation, age, instruction will make a difference. The relationship may be the coincidental. For example, the researcher may be able to find a significant relation between the increases in the number of the people who are exercising and increases in the number of the people who are committing crime. But the common sense is that dictates that any relation between these two variables must be due to the coincidence. So caution. So when average are caused instead of the individual data, the result may be the higher correlation that actually exists. So results of the correlation study using an average cannot be generated to the individuals because the averaging tends to smooth out the variability among the individual data, the values. So even if the correlation between the two variables is significant, it does not imply the causations. Okay, so that'll be all for this section. Thank you for listening.